good, like one of those big microphone things. I've thought about it because then I could get your responses in. You know what I mean? Now that you can't actually hear your responses because it's this little microphone. Okay, so as I said, I kind of changed my mind in the order in which we're doing this, but that's okay. So static electricity charging by contact, and the type of contact is called conduction. So let's continue on here. Let's define a few things. All right? And I'm hoping, and I think, that that these things might be terms that you've heard of before. And I'm going to grab a couple of these spheres. So yesterday we talked about charges, and we talked a little bit about electricity and the way it kind of functions. But we never defined any of these terms. So when it comes to electricity, there's two ways in which we can think about it. One is static. And static is when charge builds up on a substance. Technically speaking, it's not moving. All right? If the electricity, and really when I say electricity, I mean electrons, right? If the electricity or the electrons are flowing or moving through a substance, we call that current electricity. All right? And the word current makes reference to like a river's current, the flow of water. Okay? And that's because before they knew of the existence of electrons, scientists literally thought that there was something flowing like a fluid in the wires. Now again, some of you are writing ahead, but you're going to notice there's a lot of blank spaces and various things in there. And so I'll be adding some information as you go. So just be aware, the spaces are there to fill things up with. All right? So we still call it current electricity as if it's flowing like a current in a river, even though now we know it's a movement of little electron particles through the wire, okay? So when they are not moving and they've been built up on something like on a balloon, if you rub your hair on a balloon, you can get a static charge. I don't know if you know that. I'm pretty sure that's pretty common knowledge, right? But if that electricity moves, it's called current. In terms of my device, as I'm cranking this, I'm building up a charge inside these things. They're called Leyden jars. You can imagine them like buckets for charge. They're filling up with charge. And when I get them nice and full, we've got a static charge. It's not moving. It's built up. We've taken the electrons out of one bucket and we've put the electrons into the other bucket. What are you doing, Grace? What are you doing with your device? Okay. All right, that's acceptable. Once I do this, right, it's able to flow back, and that's an example of current electricity. It's flowing. I could have put a wire between them. It wouldn't have been as exciting because it wouldn't have went crack. It would have just flowed. That would have been current electricity as well. So a shock is a result of a quick removal of the buildup of static electricity. Yes? So like a wire to a light bulb is current electricity? Correct. And there has to be two wires to a light bulb. You can't see them, but inside the wire, there's actually two wires. One is going in, and the other one is coming out, because it's got to go completely through it. Yeah, that's current electricity. But if you rub your feet on the carpet, you know, build up a charge, static, as soon as you give someone a shock, click, that little spark is an example of current electricity. It's flowing at that point. Okay? All right. Let's talk a little bit about some terms that we talked about yesterday, but I need you to know, and I hope I didn't make these too small. All right? And I'm not going to draw pictures with these. It's the next ones I'm going to draw pictures with. But I thought I was going to, but I don't think I'm going to. Insulator. Oh, actually, I'm going to add on to the bottom of that. A substance that does not allow charges to flow All right? So an insulator does not allow charges to flow. And a conductor is a substance that allows charges to flow. All right? And we talked very briefly about some examples of this. What's an example of a conductor? We talked about it yesterday. Yep. Copper is an excellent conductor. Copper. We're going to find that we're going to come up with a general statement here in a moment. Yep. Ooh. Careful. I'll put tap water. All right? Because if we have pure water, it doesn't. All right? And that's more of a chemistry thing that we'll talk about later. But tap water contains impurities that allows the conduction to flow. All right? What's in tap water? What do we find that's in tap water? Yep. Minerals. Minerals, if it comes out of the ground. And those minerals are usually charged. They have usually charges on them, and they can flow. That's why tap water is able to conduct. What else is in tap water? Yep. Chlorine, to keep it, free from biological, cooties. Again, I'll use the term cooties. Bacteria, bugs, little things, right? Not bugs, but you know what I mean, like bacteria, viruses, et cetera, et cetera. And those things carry charges. And so those things can flow through the water and make it conduct. Also, some have fluoride. Have you heard of fluoride in water? Keeps your teeth strong. That can carry charges. But if the water's pure, which is very rare, but if the water's perfectly pure, it actually doesn't conduct very well. Other examples of conductors. Anybody else? Things that can conduct? Yeah, Robert? Yeah, in general, metals. Metals are good at conducting. All right? How about then insulators? Some substances that don't conduct. Robert? Excellent. Rubber. Rubber. What else? Yep. Wood. Wood. What about air? Does air conduct? Does air conduct electricity? No. I agree, it doesn't. Do you want to add something to that? Right. That's air conducting. Correct. Air, and actually, I'm going to put here air. All of our insulators, if they're subjected to enough energy, will be forced to be conductors. All right? The insulators, their electrons don't move very much. But if you pull on them hard enough, with enough charge, you can force them to move. If the air conducted electricity, as I walked past this power bar, which is plugged in to power, see that little red light? We know that that means it's on. If the air conducted electricity, I should be doing some Jedi thing right now. You see what I mean? It should be shocking me. I should be dead. We should all be dead because the electricity would all go through us. So it doesn't, okay? There's not enough power in these electrons to cause the air to conduct. If I put enough power into the electrons, I can force the air to conduct, all right? So if I put enough power into them, oh, that's so satisfying. It's the greatest thing ever. I just made the air conduct, all right, because I put so much power into it. All insulators can become conductors given enough energy. Lightning will bust right through a rubber tire. It's not even going to stop. But if I have a live wire, I could probably put rubber gloves on and grab that and be safe, right? There's a couple of things there. Okay. Charging. The term charging means that we're adding charge to an object, all right? We're adding charge to an object. Now that can happen in two ways. I can either add electrons to make it become negative, or I can take electrons away and make it become positive, all right? Okay? So charging means we're just creating a charge at some point. With the Wimshurst machine, as I crank it, I'm simultaneously building up two charges. I'm taking the electrons off of one, and I'm putting the electrons onto the other. making one of the spheres positive and the other sphere negative. So we charged both of them, okay? Discharging, the removal of charge from an object and returning it back to neutral. In this case, I can remove the charge by bringing them together and putting that charge back. How else could I remove the charge from the ball? Yep, touch it. You want to touch it? I did a little turn. Touch one of those. You did a tiny little tap. Did you notice it was a tiny little thing?
Yeah.
You see how you're giving little shocks back and forth? You're slowly discharging it. So we can touch it, all right? We can touch it. Where do the charges go when we touch it? Where do the charges go? Yep. On the outside of your skin, we conduct a little bit. It's going into our body and then ultimately to the ground, all right? So we conduct a little bit. We don't conduct a lot, but we do conduct a little bit, right? Which makes it dangerous. If you get in the middle of a lot of electricity, you can be electrocuted, right? But that's not a lot of electricity. All right, excellent. So discharging, removing it. Good. We've got our terms. Let's now talk about the ways in which we can charge. I'm going to bring this whole thing up, and I'm going to let you write it. Come on. Yeah, good. That's the end of it. Over the next, I think, 3 lessons, maybe even more, because I seem to be taking forever to get our pith balls made. That's okay. We will be testing these different methods of charging things. And we're going to test it, hopefully, with our pith balls. That's why we made them. 2 of the methods need the objects to be in contact with each other. So we say by contact. So we literally need to be touching 2 things together to either add electrons to an object or remove electrons from an object. Remember, it's all about the movement of electrons. The first thing I was going to teach was friction. That's like if you comb your hair and you all of a sudden have hair standing up on end. You might find it maybe if you're on a trampoline, you're jumping up and down, making contact with the surface. Some electrons are being transferred either to you or taken from you. It's hard to tell. We'd have to do a test. And then your hair stands on end, right? Sometimes in the winter, you're in the car, you get out of the car, you slide out of the car, and you take some electrons with you, or you leave some electrons there, you become charged. Okay, that's by friction. All right? By conduction, literally touch one charged object to another. And that's what I was doing yesterday, and that's what we want to talk about today. Crank it up, take one of our spheres, touch it, transfer some charge to it. Or take our pith ball, touch it, transfer some charge to it. So as they're in contact, either electrons are jumping on or electrons are jumping off. Okay? The last one's called induction. I'm going to talk a little bit about induction in a moment, but there's a little more to this than what I'm going to talk about in a moment here. All right. Now, when I charge an object, whether it's this big sphere or this pith ball, by contact, we will notice a particular thing take place each time. Now, I'm going to touch this pith ball so that the electrons either add on or remove off. Stop eating, folks. Put the food back. Put it back. Put it back. There's multiple people eating in this class. Stop eating. Okay. And if I crank up the Wimshurst machine and I put lots of charge on there, and I bring the pith ball close, we will notice that first It attracts to it. Did you see how it attracted to that? And if charge gets transferred to it, it should then, and see how it's sticking and sticking, it should actually repel right away. See how it keeps sticking? So this is not showing us exactly what we want to see, and the reason is, even though I'm transferring charge to it, the charge is jumping off and leaving just as quickly as it's landing on it, okay? So that's why we had to make our own pith balls, right? Our own pith balls, we want it to be really smooth, because remember, any sharp edges causes the electricity to leave. There's another thing that causes the electricity to leave, and that's water vapor in the air. And it's pretty humid in here today, so the water vapor is also discharging it. So we can see that it attracts, but it repels a little bit. There, it's starting to repel a little bit. You see how it's kind of repelling a little bit? But then it keeps going back. Let's talk about why it attracts to begin with. Why would that first pith ball attract? Induced charge separation. Write that down. I'm going to get another pith ball to see if I can get one that's going to work for us today. We'll see if we can find one that's good. That one's pretty smooth. That one's not bad. All right, let's give it a good crank so it's got a strong charge on it. If you're afraid that it's going to go crack, it won't across that big jump. It's too big of a jump. Let's bring a pith ball close. That's fun. It's touching, pushing away, and it's coming back and it's touching, and it's pushing away, and it's coming back and it's touching. Let's try this one. This is made out of a little piece of styrofoam. That one worked pretty good. All right, so it touched, and now you can see it's repelling. All right? Let me discharge it. Let me bring it back again. What does it do just before it touches? Did you see it? Watch closely. If we had a grid here, that'd be great. We could see it. What does it do just before it touches the ball? Yeah? It speeds up and it rushes to it. Do you see it kind of rush towards it? So there's an attraction first, and then it touches, and then there's a repulsion. Let's talk about induced charge separation. This is what happens before the pith ball touches the ball. For some reason, it's attracted to it. Electrons can be forced to move to one side of a substance due to the presence of a charged object. This separates the positives from the negatives. Let's draw some examples of this. Do I just have a blank slide next? Yes, I'll write it on this slide. Let's say I have an object here, all right, and it's very negative. Let's go with 1, 2, 3, 4, all right, and it's very negative, 1, 2, 3, 4, 5, 6. And I put them on the outside because we know that's where they're going to go. They're going to repel away to the outside, all right? So this is a negatively charged object. I'm going to even put one more on the end here. I'll put one more on the end. Let's bring a pith ball close to it. All right? And this is a neutral pith ball. 1, 2, 3, 4. Okay? And there are going to be 4 negatives. Remember, the negatives can move. The negatives can move around the pith ball, okay? If there is a strong negative charge right there, those negatives will repel away from the negative charge because they can move. And they will end up 1, 2, 3, 4, all on the other side. Okay? All right? So they will push to the other end because they're repelled from this end. All right? Now what that does is, inside the pith ball, we now have separated the charge. We've moved them to opposite sides. That makes this end of the pith ball more negative and this end of the pith ball more, what's it going to be? Positive. What is that positive end of the pith ball going to do with respect to the negative charged object? It's going to attract, and therefore it gets sucked in. That's called an induced charge. Yep.
But wouldn't the negatives disperse, like, away from each other?
Which ones?
The negatives on
On
the pith ball.
the pith ball, they're still going to try to get as far away from each other as possible, but now there's another push on it due to the other electrons. And so they're still going to try to get as far away from each other as possible, but they're also trying to get as far away from the other negatives at the same time, which pushes them to the other side. Okay? All right? We got that? This is still neutral, but the charge has been separated. And we call that an induced charge separation. Let's do one more picture for if we had a positive object. So what if I had a positive object, like one of the balls being positive? So in this case, I now have 1, 2, 3, 4. Yeah?
Would the negatives still be around the outside, or they will be closer to the positive?
In here,
Yeah.
they will be closer to the positive. So let's go with 1, 2. Okay? Which makes this end more positive. Okay? So this is positive. So that's a positive influence. Okay? Because they're now on the inside. We're going to bring our pith ball in. Again, the positives can't move, but the negatives can. Where are the negatives going to go this time within the pith ball? Where are they going to go? Jack? To close to the plus. 1, 2, 3, 4. Okay? Which means what would happen to this pith ball compared to that, Jack? Attract. All right? All right? Now, many textbooks in grade 9 will add a new law of electrostatics. Right? We know that like charges repel and that opposite charges attract, right? We know that. But they'll say things like neutral objects will attract to both positive and negative. Now that's not a law of electrostatics as far as I'm concerned. A neutron is not attracted to anything. So we do see that neutral objects can attract to positive and attract to negative. But it's not that there's a new special law that's formed. It's that the electrons shift and the same laws are in effect that cause it to attract. So I'm going to, again, put a negative side on this guy right here. That's my negative side. There's my positive side. All right. What I am going to put is neutral pith balls will attract to both types of charge. Okay? All right? You can see that in everyday life. If you take a comb and comb your hair and you get it charged and you bring it to some little pieces of paper, that neutral paper will attract to it, whether it's a positive or a negative. All right. So that explains what happens when we charge it up and we bring it close, it attracts, oh, that's still charged. See, that's still charged. Let's get rid of it. Bring it close, it attracts, it touches, and it repels. Yep.
If you were to put that info on the positive one and then put it on the negative one, would they like go together?
What will what go together?
Like if you put the pistol on the positive one.
Yep. I got to check, see which one is officially positive. This is officially positive. Yep.
And then you were to put it right onto the negative one.
Yep.
Right away. Would they attract?
Well, yeah, because it's now become positive. Let's first talk about what happens when they touch. That's our next move. Charging by conduction. So we've now explained why it's coming together, why it's coming close. Let's talk about what happens when they touch. Well, when they touch, electrons can be transferred. Okay? So when they touch, electrons can be transferred. And this is the simplest of all charging. Take an uncharged object, bring it in contact with something that has a charge, and electrons get loaded on it or taken off. I'm just looking ahead to my slide. Excellent. Good. Yep. Electrons. Well, that's what the charge of an electron is. Yeah. Electrons are negative. They're the little things that can be moved around easily. And they're way on the outside. Yep. Nope. All right. Let's talk about bringing, what is my next example for those who are looking ahead? A negative to a neutral. A negative to a neutral. This is my negative one according to what I've tested. If I bring a negative to a neutral, it attracts because it's neutral, right? So they're shifting to the other side. It touches, and then what does it do? It repels. What happened to the electrons on this negative guy? Yep. They jumped onto that one, which now makes them both negative, and therefore they repel. Okay? So transfer or conduction is simple. It's a simple transfer of charge. You don't necessarily need to write that on the bottom. You can, but my picture is going to look like this. I'm going to take my negative objects. 1, 2, 3, 4. I'm going to put lots of negatives on them. I'm going to count them though, because this is important. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right? We get the idea that it's going to attract, so I'm going to have it touching it right now. I'm going to have the other fifth ball touching it. 1, 2, 3, 4. And we know that its 4 is over here. 1, 2, 3, 4. Because they were induced to the other side. And now, as Jessica says, they're going to jump over there. So some of the electrons are going to move. The reason I'm counting them is, in the end, I can't have any extra electrons or electrons disappear because that can't happen in the universe. Electrons don't just appear and disappear, okay? So in the end, they're now going to repel 1, 2, 3, 4. How many electrons in total do I need in both of my objects? I can't just create them and have them disappear. How many in total do I need? Yep.
There's 10 in that one.
Yep. So how many in total do I need? Yep. Well, very good. They will equalize out to charge. You've done that correctly. It'll end up as 7 and 7. Very good. But I have to have 14 in total. Okay? So 7 and 7. That's correct. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right? That's good. You're correct. They will spread themselves out. Mathematically speaking, we could say we started with 4 electrons here. Sorry, no, don't do that. No, I don't want to do that math right now. Actually, we can do the math. Question, Danton? You would then conduct them to the ground, and then the whole process would stop. You would interrupt it and conduct it to ground, and they'd both become neutral. You would have sucked the extra electrons off of everything. Okay? Let's do the math, though. What's the charge on this one initially? The total charge, not the number of electrons. What's the total charge on this ball, taking into account the pluses and minuses? What's the total, Jenna Lee? We don't add them because they're like integers. We add them like integers. Let me change that. So we've got 4 positives and 4 negatives. So what's the total charge? 0. This has a total charge of 0. What's the total charge on my negative thing to begin with? We're doing it like integers. Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. -6. -6. Excellent. Good. We touched them and they moved. What's the charge on this now? -3. What's the charge on this now? Yeah? -3. That will be true every time. That will be true. We've got to take into account the pluses as well. So we have to add them like integers. In the ball on the left, there is a +4 and a -7, resulting in a -3 overall charge. All right. You can write down the bottom part. So we've now explained why it attracts due to the induced charge, it touches, it transfers, and then it repels. That's why we see that. Okay? And I'm hoping when we do some tests next week, we will see the same thing. Let's do a positive to a neutral. I'm hoping that the yawning is because this is so easy. Oh, that's unfortunate. Now, with only using 4, the math becomes tricky, but let's see if we can still do it. 1, 2, 3, 4, and I'm now going to just put 1, 2 in the middle. Right? Because remember now the pluses are sucking those electrons in. We're going to go with 1, 2, 3, 4. And just before it touched, remember we induced the 4 over to that side. Right? Remember they kind of got sucked over there? Okay? In terms of electrons, what's going to happen in this case? Describe to me what's happening to the electrons in this case. Jay, what's happening to my electrons in this case? Which way? Are they jumping into the pith ball? No, they're not, because those negatives are not gonna want to get close to those negatives. So they're not going to jump into the pith ball this time. What's that? The pith ball ones are going to be attracted to these pluses. Okay? I guess the question becomes now, how many are in each? So this time, electrons are going to leave. 1, 2, 3, 4. I'm just putting my pluses in. How many are going to be in each, Danton? So in total, you're right, we had 6. 3 are going to go in each. 1, 2, 3. 1, 2, 3. So they spread each other, they spread out evenly. What was the original charge of my pith ball? Just tell me. 0. What was the original charge of this guy? +2. What's my final charge? +1 and +1. Okay? And now they repel. Yep.
Do you want us to always put like a +1 or just write 1?
Oh, you could just write 1. Plus is sometimes left out. It's okay. Yeah. All right. Let's do one more example before we do homework. Let's do a negative to positive. Let's do a negative to negative if we could force it. No, let's do a negative to positive. Let's do a negative to positive. What's your question?
On the last one, if
for those who are wondering what's happening. And this time I'm going to use two balls. I'm going to use 2 spheres, as if I touch them together. My picture is going to look like this. Okay? What is it?
is it positive or neutral or 0?
0 is neutral. Positive 1 is positive by 1.
Oh, right. That makes sense. Okay, never mind.
Let's do a negative to positive. Let's say I took this crank, all right, and I touched 1 to the negative, made it negative, just like it transferred, just like before. And now I crank this more, and I make the positive one a little more positive. So they're different numbers. So let's say I had 1, 2, 3, 4 with 1, 2. All right? And I'm going to bring it in contact with a 1, 2, 3, 4 that then has 1, 2, 3, 4, 5, 6. And I apologize, I wanted to spread them out nicely. I didn't, but I should have. All right? And they're going to touch. And then they're going to separate. What's the charge on this guy on the left? +2. Excellent. What's the charge of the guy on the, oh, let's put a 7, 8. 7, 8. Because I didn't want them to cancel out completely. You'll notice I would have canceled out completely. So I added 2 more electrons because I wanted them to be different charges. All right? Because it would have been a positive 2, right? And I didn't want that. So what's the charge on this negative guy now that I've added a couple extra? I got 4 and 8. What is the charge? Yep. Negatives. I got 8 negatives. -4. -4. So that means the negative's a little bigger than the positive. So when they touch, the electrons try to spread themselves out. What am I going to end up on each after they touch? What's going to end up on each? How many electrons in total are there? Yep. There's 10, and they're going to try to get as far apart from each other as possible while they're touching. How many are going to end up on each? How many are going to end up on each? What do you think, Jack? 5 each. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Well, flip it around. It's negative to positive. Is it a negative to positive? Oh, goodness. What's the charge now on our new objects? -1 and -1. Oh, no. Yeah, -1, -1. Okay? All right? So they will equalize themselves when they touch. All right, we're almost to a bell. There's a little bit of homework. Write that down. I'm not going to do a negative to negative. Again, they would equalize themselves. They would shuffle until they equalize. Let's take a look at one interesting phenomenon, though. Jess wanted to know what would happen if we put the pith ball in between the two. Let's think about that. You did, actually. Let's think about that for a moment. So, if I take this pith ball, this one's working really good today, and I give this a good crank, and I crank it up just enough before it goes crack. All right. And you're in a perfect spot for this. Okay. So, if I touch this to here, it's going to attract. Oh, it's already charged. Whoa, there we go. And notice it's repelling. Now, notice it's really attracted to the other guy. Why is that? What's that? And the other one is negative. So if it touches here, then what charge is it going to become? And then it's going to repel away again. Now where's it going to want to go? Back to the other guy. Come on, touch. Why don't you want to touch? That's exciting. If I bring these close enough together, what should the ball do?
Stay in the middle.
It's like it's dancing. Here, let's try it with this guy. Number 3 and 5.
Hi, coming back after
What for?
I found to ask you something.
Oh, let's take care of it on Monday.
Okay.
Let's take care of it on Monday. Chloe also did. If you have questions about your test, we can take care of it on Monday. All right? Okay? Did you catch all that? Come at lunch. I'll do some math with you. Okay? Come at lunch.
Are you going to post those on Classroom?
Post what?
The questions?
I can put them on Classroom. Yeah.
Because I was looking for them yesterday.
Yeah, and I forgot to do that. I got to stop my video here.